Howdy Calc AB, I'm back. I'm here to make another video for you guys that deals with some of the work that we've been doing in terms of differentiating, integrating with exponentials and logarithms. Only now, instead of Euler's number being the base of the logarithms, we're going to talk about other bases. And I got to be honest, it really isn't going to be any different, because what we do is we take a base that's not Euler's number, and if we're going to do some calculus with it, we turn it back into Euler's number. So let's start off by a quick review of some things that are true of bases other than E, and then we'll just kind of go from there. I'm going to just start off with some of the real basics. For example, if we have a base that's not E, like 3 to some power, and let's say it equals 1 over 81. Okay, and we want to solve that. You've got a couple of options here. One is to try and write 1/181st as a power of 3. Well, we know 81 is 3 to the 4th power. So, this could be as simple as saying, hey, that's 3 to the -4 power. That's 3 to the x. Take a log base 3 on both sides, and there you go. You get x equals -4. Okay, that's easy peasy. It's just using a different logarithm base every time you have a different exponential over there. The problem is, as we start to develop our techniques, for calculus with this stuff, I don't want to have to keep going back to these different formulas and everything. And so what we learned back in Algebra 2 was there's actually a way to change the base. And there's a way to change base for both exponentials and for logarithms. Now, I think you're probably familiar with the change of base for logarithms more so than you are with exponentials. So let's remind us of what that change of base formula is. And then I'll show you how we would use that for some of our calculus. So logarithms. To change the base of a logarithm, then you take your original log base, and for whatever reason we don't like log base b, we can change. We can change to any base we want. Let's call it log base a. You take log base a of the original argument, divide by log base a of the original base. Now for us in calculus, right, what base are we most comfortable with? Well, it's probably natural log, right? Well, that's just a different base of our logarithms. It doesn't matter how you want to do that. Whatever the new base is, you can go to natural log. Just do natural log of x over natural log of b. Remembering that natural log of b is probably a constant. Yeah, so when you're deriving or integrating, if you need to change the base for the logarithm, change it to natural log. What you really get is this constant 1 over natural log of b times the natural log of x. And that's handy, because then that 1 over natural log of b is just a constant. So if I had to take if I had log base 5 of x, and I was supposed to take the derivative of that, well, I would just change the base. That's the derivative 1 over natural log of 5 times the natural log of x. 1 over natural log of 5 is a constant. So it's 1 over natural log of 5 times the derivative of natural log of x, which is, of course, 1 over x. And there we go. That's how the change of base helps you take the derivative if the base is not already natural log, okay, not base e. And I think that the change of base formula that for logarithms is something that you're used to. Change of base for exponentials is a little bit trickier, okay? It's probably not one you've seen as much. Change of base formula for exponentials. Okay. Now the key to this is to remember that a logarithm is just an exponent, right? So if I have a to the x power, and I don't really like a, okay? A is a bit of a pain. Well, then what I'm going to do is I'm just going to raise it with an inverse like so. A to the x is equal to e to the natural log a to the x power. Okay. Yeah, because this is basically saying, hey, what exponent do I put on e to get, a to the x power, and then put that on e, so you get a to the x power back out. Yeah. Now, the cool thing about this is you can actually use your properties of logarithms. Oops, that's supposed to be an e. There we go. And you get a x times natural log of a, which again, I like this product here because natural log of a is just a constant. A is just some constant base being raised to a power. So if I'm doing a calculus problem, and let's say I have 4 to the x power and I'm supposed to derive that, well, I don't really like that. Okay. Let me rewrite it as e to the x times the natural log of 4. Well, that's just a constant times x. And we know e to a power is just e to that power again times the derivative of the power. Now, this is natural log of 4 times x. Derivative of x is 1 times natural log of 4. So we get natural log of 4 times e to the x natural log of 4, which is natural log of 4 times 4 to the x power, if you want to come all the way back to the base being 4. So when we have bases other than e involved in the calculus part of things, really, ultimately, what we do is we change the base back to e. If it's an exponential, well, there's your change of base formula. If it's a logarithm, hey, we've got to change a base formula for that as well. Okay, right here. And that's how we will handle most of the calculus with the base that's not e. Now, there's in this section of the text here, this is at 5.5, we have some work in here about different applications with bases that are not e. I'm actually going to say let's not worry about that right now, okay? Because we have more work with applications coming up later in the chapter that really we use Euler's number for all those applications anyway, so it's just easier if we just save it all for the end. There's only one formula for compound interest that we might use a base that's not e. Even then, we can sort of explore how e would make that work. I need to talk to you a little bit about integration with these. Now, one thing we have not done yet, and we won't do for quite a while, is we haven't integrated natural log of x, so don't worry about that. But what we might see in here is a base other than e being integrated in an exponential. Okay, so if I had like an integral, of say 2 to the x power dx. Okay, well again, change of base formula for that. Let's apply that. That's the integral of e to the x times natural log of 2 dx. And again, this is e to just some power. We normally would sub that power out. Well, really, what we're doing is we're saying, hey, let's write it out this time. If if u is x times natural log of 2, then du is natural log of 2 dx. And so we don't have a natural log of 2 in our integrand here. So we'll bring in the natural log of 2, which means simultaneously we will divide by natural log of 2. And now we have e to the u du, which again, we love e. It's the easiest function in the world to integrate or divide. That's just e to the u, which is, of course, 1 over natural log of 2. E to the u, which is x natural log of 2 plus c. And if you want to get real fancy, you can do 1 over natural log of 2 times 2 to the x plus c. You can remove e from it entirely by changing the base back to 2 when you're done. It's not wrong to leave it as e as the base, but it's nice and compact and simplified if you do that. Bring it all the way back to 2. Okay, let's see. With the natural log function and integrals, we're not going to do that, so don't worry about that part right now. We need a little bit more practice with integration before we're ready for that. There's another technique involved in that, one that is not really part of the AB curriculum before the AP exam. It's something that we'll do in AB after the AP exam. for those of you that are going on in calculus, you'll be well served by knowing how to use the process called integration by parts. And that's how we do the integrals that involve logarithms. So most of the integrals today are going to involve these exponential functions. All right. Let's do one more together, and then I think it'll be time for you to go and try some of these problems. If y is equal to x to the x power, and we're supposed to find dy dx. Okay. This is one of those times when you're not really going to be given a whole lot of choice in terms of how to proceed here. Okay, because it looks deceptively like our previous problems where we have a base other than e, except that the variable is both the base and the exponent. Okay, and that is a huge red flag for us because the variability of both the base and the exponent mean we can't just replace the base with a constant. Okay, so how do we proceed? Well, there's a technique we taught you earlier in chapter 5. It was on the quiz. It's called logarithmic differentiation. That is really the only way to handle when you have a base that has a variable in it and simultaneously the variable is in the exponent position as well. So we need to use logarithmic differentiation here. Okay, so as a reminder, what that means is you take a logarithm on both sides. Now, what base should we choose? Well, it doesn't really matter because you could change the base to be natural log any time, but if you get to choose the base, why not make a natural log from the outset? I agree. Let's do natural log. Okay. Now, why do we use logarithmic differentiation? Because the rules for the exponents in logarithms allow us to bring down that x from the exponent position, and we get x times the natural log of x. So this is the one. Whenever you see a power that's an exponent and the base, or power that's an exponent, I'm sorry, a power that's a variable and the base is the same variable, and that's the variable you're differentiating with respect to, you're gonna have to use logarithmic differentiation. Okay, now on the left-hand side, that's easy. Derivative of natural log of y with respect to x is just y prime over y. On the right-hand side, now we have a product. We have to use the product rule. The derivative of x is 1 times the natural log of x plus x times the derivative of natural log of x, which is, of course, 1 over x. So we have y prime over y is equal to natural log of x plus 1. Now, as you know, we are not done. We have to solve this for dy dx. So I'm going to bring the y over to the other side. I'm going to multiply by y on this side. And I'm going to multiply by y on this side. Okay. So the y's cancel here. And I know it was a subtle thing I did right there, right? If y is equal to x to the x power, yeah, let's go ahead and use that when we bring it over to this side, right? That's y right there. So we get x to the x power times natural log of x plus x to the x power, or you can leave it in its factored form. But that's how we have to handle the problem when we have the variable in both the base and exponent position. So that's why I wanted to do one more example with you. All right, guys, I've hit quite a few of those change of base issues pretty quickly here. Of course, you can always rewind the video, go back through, but that's it for today. So thank you, guys.